a brief tutorial on work in situations where there are multiple forces at play on March 9th, 2017. Okay, so we have this object with multiple forces acting on it. As always, the first thing to do, as sad as it may seem, is to draw all the forces on the object. Force applied, of course we have a normal force. So that's always your first step. So we can look at each of these forces individually and decide what work that force is doing on the object. So we have multiple things here. We have the work done by gravity, the work done by friction, the work done by, the applied force. The axis that this thing is moving on, if we do our standard thing of tilting the axis, no, I'll get rid of that. The work that's happening on this thing is all happening on the x-axis. There's no work happening on the y-axis. So there is no work done by normal force, and there's no work done by force of gravity on the y. That's important. All the work is done by forces that exist on the axis on which the motion is occurring. So we have three forces that are acting on the axis on which the motion is occurring. We have F of gx, Fk, and F applied. Good place to start. To look at the work done by each of these forces individually, we do this. We say work done by gravity is equal to force of gravity, we need to specify that it's on the x, times the distance the object moves, times cosine of theta, where theta is the angle between, theta is the angle between the force and the delta x, the displacement. Okay? So in this case, because gravity on the x is moving it this way, but its overall motion is going up the ramp, we're told, the angle between the force of gravity and the motion of the object is 180. I know. Okay, so force of angle between the motion and the force. You look at the free body diagram, and in all cases, the force that's doing the moving is only the portion of the force that is parallel to the motion. So, in this case, the only part of gravity that is parallel to the motion is the force of gravity on the x-axis. The force of gravity on the y-axis is perpendicular to the motion. It's not doing anything. So, when it's in the basically backwards, this is going to be 180. So, force of gravity on the x is mass, gravity, and this is, let's say this is 15 degrees, then that's going to be sine of 15. If this thing has moved, let's say our delta x is 5.0 meters. I'm making up numbers. This is not quite number 5. Then that would be times d. Oops, I got to shrink this. And that's times cosine of 180, which is just going to be a negative 1. We're just saying that the work being done is negative to the motion. So we'll say that the mass of this object is 10 kilograms, so we're going to take 10 kg times 9.81 meters per second squared times sine of 15 times cosine of 180. So what do we have? Okay, we have the work done by gravity showing up as negative 126.9507, blah, blah, blah. It's negative because the work that gravity is doing is in opposition to the direction this thing is moving.
So do we just
Gravity is,
negative, or do
no,
just
we use this cosine of 180, which is negative 1, and that gives us a negative number. I said 5.0 meters was how far it moved. Delta. I'm not doing number 5. I'm making up numbers. Sorry. I'm doing examples, but it's not exactly number 5. Okay, so the work done by gravity then is negative, and if I gave myself two sig figs here, work done by gravity would be negative 130 joules. Okay? Okay, so we figured out that first part, the work done by gravity. What about the work done by friction? Because there's also work done by friction, which is also basically retarding the motion of the object. It's acting in opposition to the direction that the object is moving. So we can do work done by kinetic friction. Well, that's going to be equal to the force of kinetic friction times the distance the object moved times cosine of theta. And again, theta is theta between the force and delta x. This thing's moving up the ramp. Friction is trying to stop it from moving up the ramp, so that's going to be cosine 180. This is easy because we're just given very often the force of friction. There are some cases where we do have, we're given a coefficient, we have to figure out the force of friction, but you know how to do that. So in this case, let's say the force of kinetic friction is, I don't know, 23 newtons. So the work done by kinetic friction would be 23 newtons times 5.0 meters times cosine 180, because friction is also working backwards on this object. If you're just flat out given the force of kinetic friction, it's really easy. You plug it in, yay. In this example, the work done by kinetic friction would be 115 joules. Okay. What if we're not given the force of kinetic friction and instead we have to figure it out from a coefficient? Okay, so let's say we're just given a force of, or a coefficient of kinetic friction. Let's say it's 0.111, pretty low friction surface. This is a pretty smooth ramp. How would we find the force of kinetic friction? Well, we do sum of forces on the y. I know you thought you had left that all behind you, but you didn't. And we have, well, okay, back that up. We know that mu k equals fk over fn. So we know that mu k fn equals fk. We have mu k, we need to find fn. In order to do that, we do sum of forces on the y. We know that fn, minus fg equals 0. Therefore, fn is equal to fg. Fn equals mg. So I'm going to get rid of all this extra stuff now. Cut. Cut. Shrink. Shrink. Oh yeah, I'm sorry. Yeah, mg cosine of 15. Yes, my apologies. So, what we have is that the work done by the force of kinetic friction is equal to mu k mg cosine 15. That's a mouthful. Times distance times cosine of 180. And it's important to keep your thetas straight here, because if you screw up your thetas, all hope is lost. Not really, but... Okay, so if we plug in numbers. Okay, so I get a work done by the force of kinetic friction of negative 52.1165, on and on and on, joules. So with two sig figs, it would be negative 52 joules. Okay. Feeling better about these? Okay. So let's do the last component of forces that's doing work. Okay, so the last force here that's doing work is the pusher, whoever's pushing this thing up something. So the work done by the applied force is equal to the applied force times the distance it moves times cosine of theta, where you could just hit play on this now. Theta is the angle between the force that's doing the work and the motion of the object. In this case, the pusher is pushing it up the ramp, and it's going up the ramp, so that's cosine of 0. There's a 0-degree angle between those two things, which means we can actually ignore that. Okay? So, I didn't tell you what the force applied is. Let's say that it's, I don't know, 253 newtons. Lots of force. So, the work done by the applied force equals 253 newtons times 5 meters Okay, so the work applied then is equal to 1,265 joules. We only have 2 sig figs, so we would say 1,300 joules. Now, here comes the really cool part, the net work. Here's the kicker. Work net equals force net times d cosine theta, where theta is the angle between the net force and the motion. Well, you can go to all the trouble of figuring out the net work by doing sum of forces, or you can say that the net work is equal to the sum of all the other works. You can take your rounded answers and just figure out your net work that way. So either way is legal, either way works. That's it.